like to thank all the people here to join us. And this is the last of the series of our seminars. So this is a collaboration between IMT-Atlantique and RIKEN. And we have a memorandum of understanding for collaboration between RIKEN and IMT-Atlantique. And every year we do the real event workshop for a few days in Brest, IMT-Atlantique. But this year it's impossible, so we decided to do something that we can do at this moment. So this is a seminar series. Because of the time difference, we have 1.5 hours every time. And the first seminar was me. I talked about our work in RIKEN, and from the second to the fourth, we have a talk from IMT-Atlantique and another one from RIKEN, and followed by discussions. And this is the last one given by Pierre from IMT-Atlantique. So thank you very much again for joining us. And Pierre, so would you like to start your presentation? Thank you.
Yes, thank you, and good morning, good afternoon, everyone. Thank you for joining to this last webinar. So here I decided to present something new for me. I'm working actively on that for only 1 year, and I want to explain you what it is and what are what is the link with data assimilation. So here I'm working on climate projection, and we are trying to narrow the uncertainties in climate projection. And the idea is try to use advanced data science tools like data assimilation, analog forecasting, and model evidence. So I will try to explain you during this presentation these tools and how we can combine them to make some we hope to make some better prediction of climate indices in the future. So this work is a collaboration with different colleagues from applied math, also from oceanography and climate. So really there is a mix between mathematician and physicist, and the idea is try to do some data science with physical point of view. So, so this is the objective of our study. So you see that here you have the present days, and here you have the future. And the idea is try to make a prediction of different climate indices in the future. So a climate index can be, I'm sure you know this kind of climate indices. It can be, for instance, the global mean temperature for the from now until, for instance, 2100. So this is a well-known climate index. And so to get this kind of curves in the future, we use what we call the CEMIP simulation. And CEMIP simulation are basically GCM models. So they are meteorological model that we run for a very long time. And to get this kind of uncertainties in the climate indices, we use a lot of different runs. So this is an ensemble of runs. And these simulation are coming from different models from different countries. And for each model, you have different members coming from maybe an initial condition which is not exactly the same. It's also coming from different parameterization in the model. And you have also some different scenarios, because in the future, the CO2 emission have a great impact on this kind of time series of climate indices. So at this moment in the IPCC community, what people use is unweighted projection, meaning that all the simulation have exactly the same weight. So this is a one model, one vote strategy, or also called the model democracy. So basically, the result of the IPCC will be this black curve, which is the mean or the median of the different simulation. And you see that, so this is the unweighted mean, and here you see the unweighted spread. So this is basically the empirical standard deviation of the different simulation. And what we want to do is try to do a weighted projection. So instead of using the model democracy, we want to say that maybe there are some simulation which are better to describe a climate index, and maybe some other simulation like the blue one here, which is not very accurate. So we want to put a weight to the simulation, and the red curve is the weighted mean, and you have also the weighted spread. So you see that the spread is reduced, and the mean is different. The red line is different from the black line. So this is the objective of our study. And so to weight the simulation, we will to compute some weights, and to compute the weights, we will have to see to compare the simulation to the real observation we have from the current time and the past time. So during a historical period of measurement, we will try to see which simulation match well the observation, and if a simulation is good to reproduce the observation variation, we will give a strong weight to this simulation. And if another simulation is bad at reproducing observation, the weight will be low. So this is the idea. So if you have any question, do not hesitate to interrupt me, okay? So you have to know that the CEMIP simulation, as I said, so there is an ensemble of simulation, and here you have the mean temperature over a given location, and you see the ensembles, and this is just to show you that there is a strong variability in the ensembles, and also you have strong differences in terms of CO2 emission scenarios. Okay, so here you have the business as usual scenario in red, and here you have the opposite scenario in blue. What you have also to know is that in climate simulation, there are three kinds of variability that we need to differentiate. So the first one is what we call the internal variability, and it's important at the beginning of the at the short-term horizon. Sorry. So the internal variability in yellow in orange is due to the chaotic effect of the system, meaning that, so why we have this kind of variability? It's because we don't measure everything currently in the present time. So we are not really sure about the initial condition nowadays. So that's why we have this kind of chaotic effect here, and this is called the internal variability. Then you have the model uncertainty in blue, which is more important in the decadal horizon. So this is due to basically some parameterization inside the models. So there are a lot of parameterization, and there are a lot of uncertainty in the parameters of the model. So this is due to, so this is the blue uncertainty. And finally, you have the long term impact of the scenario uncertainty. So this is due to the different scenario we use in terms of CO2 emissions. So okay, so here I will focus on the blue part, so meaning on the decadal horizon and also on the parameterization inside the model. And as it has been said in this nice paper, there is really a potential to narrow the uncertainty, especially in the model uncertainty, so the blue uncertainty. And also we will focus on regional aspect of narrowing uncertainty. So this is important in my talk. So at this moment, a lot of people are using a methodology trying to narrow the uncertainty in the IPCC community. So this is the emergent constraint method. And so this is a very simple method and easy to understand. So I think that's why a lot of people are using that in the IPCC community. So the idea is try to narrow the uncertainties in the climate prediction. So this is exactly the goal of our study, but they are doing that without weighting the simulation. So this is another idea, and I will try to explain you. So so what they are doing is trying to make the relationship between a climate index nowadays, for instance, the mean temperature nowadays versus the mean temperature, for instance, in 2100. So there is a big DT, so 80 years between the X and Y axis. And the blue points here are the CMIP simulation. So the blue points are just what we are just reporting what the model says for the global mean temperature nowadays and in 2100. So using these samples, people are adjusting what we call an emergent relationship, which is most of the time linear like this. And then using this relationship, they will project the observation of, for instance, mean temperature. They will project this temperature into the future. Okay, so this is the observed mean temperature. You see that there is a variability here because we don't measure exactly the mean temperature, and this mean temperature is propagated in the future using this relationship. So you see that the result of emergent constraint is something narrow, meaning that this Gaussian distribution is has a low variance compared to this one. And this one is basically the variance computed using the model democracy, meaning that all the parameter, all the simulation have the same weight. So you see that emergent constraint is trying to go from this distribution of for instance, the mean temperature in 2100 to this distribution, which is, I think, better. But I think this method is very questionable. A lot of people are using that, and there are a lot of issues, I think, for me. So first is a low number of samples to adjust a linear regression. So to adjust a linear regression, I think it's okay. But you see that what is important in this technique is the estimation of the spread around the linear regression. Because this spread is used to propagate correctly the uncertainty of the observation. You see that, so this is the uncertainty of the observation, and we use the spread of the linear regression to propagate the uncertainty of the climate index. And there is a problem in most of emergent constraint studies because they use a linear regression with what we call homoscedasticity, meaning that they assume that the variability is the same everywhere in the regression line. But here you clearly see, in this small example, you clearly see that maybe we can be confident in this spread where there are a lot of samples, but in this part of the scatter plot, we are not confident with the estimated spread. It should be very large here, and maybe also here, which is very important in our case. So the last also issue, I think, is a big DT between the two climate indices. So here we are nowadays here, and in the y-axis we are 80 years ahead, and this is very, very large. And is there really a causality effect between these two climate indices and with a very large horizon? I'm not sure. So what we want what we propose here is something different, and basically we are trying to reduce the DT between the x and y axis, but the idea is quite similar in what we propose. So basically now we are trying to make the relationship between a climate index at time t and a climate index at time t plus dt, but the dt here is very, very small. It can be, it's less than 1 year. And so the idea is to try to see the SEMIP simulation if we find some differences in terms of the relationship between two consecutive times. And this is an illustrative scheme to explain you that in a lot of dynamic models there are some differences in terms of dynamics or short-term dynamics. So this is an example using the Lorentz 96 model, and we are changing the parameterization of the model, and you see that using different parameterization we have different relationship between two consecutive times. So the difference is not important in the middle part of the distribution, but the difference starts to be important in the extreme part of the distribution, so extremely low and extremely high. So in that part of the distribution, you see some differences in terms of model dynamics. Okay, so this is really what we want to focus on this project, try to see some differences in the SEMIP simulation, especially in the extremes. And so then I will explain my idea. The goal is trying to see if some forecast given by the numerical simulation, if these forecasts are close or not to the observation. So this is the observation in black. So basically, when we will get one observation, we will compare this observation to the forecast from the coming different models. And here you see that the forecast coming from the blue model is better than the forecast coming from the green model. So we can compute a likelihood, and this likelihood will be used to compute then a weight. So basically the weight for the blue simulation will be higher than the weight for the green simulation. Okay, so this is the idea of our project. Try to use some forecast, but this is very important. These forecasts are not pure physical forecast coming from a GCM model. It will come from analog strategies. So the analog strategy is quite simple. We assume that we have a lot of available numerical simulation from different models, and we will copy paste some trajectories in these catalogs of simulation, and when we copy paste these trajectories, we can get some probabilistic forecast like this, and we can compare probabilistic forecast to the observations. Okay, so now you will say that, okay, but to get a good forecast, we need to get a good initial condition at time t minus dt. So this is time t here, and this is the previous time t minus dt. So this is very important indeed, because we need to get a relevant forecast. We need a relevant initial condition, right? So this is what we do here. So to start from the best initial condition we can, we will do some data simulation, and this is really the role of data simulation, is to get the best initial condition at time t in order to get the best forecast in the future. So this is the methodology we want to develop. So it is based on A, data simulation to start from a good initial condition, B, to apply the analog forecast to get a probabilistic forecast like this, and C, it's to compare the forecast with the observation, and the goal is to compute a weight at each time step. We want to compute the weight and to see if one simulation is better than other simulation. And we will repeat again and again during this observation, as when we will repeat this using all the observation we have in the observation period. Okay, so so this is the 3 points I will try to develop, and you will see that there are some studies dealing with the combination of these 3 points. So the first study is the combination of data simulation and the distance between observation and forecast. So this is A and C. So this has been introduced by Karasi in 2017 in the context of detection attribution in data simulation. So what is detection and attribution in climate? It's something not easy to. So the idea is try to see if observations here are coming from the factual model or a counterfactual model. So basically, the factual model can be the model with CO2 emissions, and a counterfactual model can be the opposite, the model without human activities. So the idea of detection attribution is trying to say if the observation, what we observe, is due to human activities. And so this is exactly what we want to do in our project. So we want to compare different models to observation, and we want to use data simulation to do that. So what they use in this paper is what we call the innovation likelihood in data simulation. So the innovation likelihood is based on the innovation, which is the difference between what we observe. So this is the red cross, and the forecast. So this can be the blue or the red forecast. So the innovation should be close to 0, right? If you want to get if the forecast is matching the observation, the innovation should be close to 0. And if the innovation is close to 0, the likelihood will be high, and we want to maximize the likelihood. So this is the idea of this metric. And you see that in this metric, so you have a kind of a squared of the difference, and there is a normalization here by using a covariance matrix. And this covariance matrix is very interesting, because there are 2 parts in this covariance matrix. there are two contributions, one from the error coming from the observation. So this is the observation noise, basically. And this is the spread of the forecast. So basically, how confident we are in our forecast. So you see that in this metric, distant metrics between observation and forecast, we take into account the uncertainty in the forecast and also the uncertainty in the observation. Meaning that if we are not confident in our observation or in our forecast, this innovation will not play a big role in the computation of the likelihood. And at the contrary, if we are very confident here and here, the innovation will have a strong impact on the computation of the likelihood. So so this is the first ingredient, the combination of a data simulation and a nice distance between observation and forecast. The second ingredient is the combination of data simulation and analog forecasting, A and B. So this has been introduced at IMT-Atlantique, and this is very simple. So this is the data simulation mathematical equation. So you have the dynamic model here, and you have the observation equation here. And with the idea of ONDA, so this is the analog data simulation, is to replace the dynamic model by a kind of statistical emulator of the dynamics. So I will try to explain you the concept here in the case of ensemble Kalman filtering using the Lorentz 63 model. So in an ensemble Kalman, if you are at time t minus dt, so we are here at the previous time. So we use some members to track the Gaussian PDF of the state of the system. Okay, so basically the mean, the empirical mean and empirical covariance are used to get the distribution of the state of the system using the 5 members. So in the ensemble Kalman filter, for each member, we will apply the dynamic model and we will get a new forecast for each member. And then we will combine all these members to get the empirical mean and empirical covariance. And this is the idea of the analog data simulation. This is exactly the same for each member. We will try to get some forecast, but the forecast will not directly come from a numerical equation. It will come from a statistical emulation. And this is based on the analog forecast. So we will use a lot of historical runs of our model. So we assume that we have recorded a lot of simulation of our system, and we will try to find similar situation of this member in our historical simulation. So maybe we will find, I will take the green example, sorry. So for this member, we will find, I don't know, 10 analogs in the simulation, and we will have a look at the future of these 10 analogs. So this is the successors in time. So basically this is time t and this is time t plus dt. And then we combine these successors to get a forecast. And finally, we can compute an empirical mean and covariance. Okay, so this was A plus B. And what happened if we combine A plus B plus C, meaning data simulation, analog forecast, and contextual model evidence, so distance between forecast and observation? So this is what we have done, and this is new in the literature. So we tested this approach in a simplified GCM, which is called the SPEEDY model. So the SPEEDY model is a simple GCM with a low number of levels and a low number of grid points. but you have some physics inside, and especially you have some parameterization of the convection. And if you remember, my objective is trying to see if we are able to detect some changes in the parameterizations. So this is what we will focus on here on the convection. And especially we will work on this parameter, which has a strong importance in the convection activity. So if this number is high, the convection will be strong and rapid. And if we reduce this number, the convection will be less important. So we define 3 values for this parameter, and what we call the true model. So what we want to retrieve, so the true parameterization is this value 0.9. So this is just an example to show you the impact, this sensitivity study to show you the impact of the changes of the parameter. So here you have the temperature and the precipitation for the true model, and here you see we see the anomalies between the climatology of this model and this parameterization. So you see that in terms of temperature, we start to see some differences between the two parameterization and also in the precipitation. And if we increase the difference in the parameterization, we also increase the impact on the temperature and the precipitation. So this is just to illustrate the impact of the parameterization. Okay, so now the details of the experiment. So we are using the ensemble Kalman filter with 40 members, and we are using adaptive inflation, which is quite common in data simulation. And so, as I said before, here we are using the analog forecast. So meaning that if we use analog forecast, we need a catalog of simulation. So we will not run anymore the speedy model to get some forecast. We will use speedy or simulation records to do some forecast. And this is what we have done here. So we have generated some catalogs, very long-term catalogs with the 3 parameterization, including the true parameterization, which is here. And then we generate some observation coming from the true model, okay? And we just put a noise on this observation, and this noise is more or less the noise we have in the satellite or in situ measurement of temperature. Here we are considering observation of temperature. So you see that observations are coming from this parameterization, and we add a small noise. The idea is try to see if we compare this observation to this catalogs, are we able to say that the observations are really coming from this parameterization and not this one and not this one. So this is our goal here. So to do so, yes, just have to explain that we applied the analog data simulation on 3D local domains. So this is very important because analog data simulation, the great advantage of this method, of the combination of A and B, is that we can apply the forecast on a very short domain, local domain, instead of the whole state of the system. Okay, so we don't need to run the assimilation for everywhere in the globe at every location. We can do that very locally because the analogs are local analogs. So this is a very important point. Okay, so this is the kind of result we have after applying the A and B. So after applying analog data simulation, you have the true values coming from the parameterization 0.9. And this is the result in blue and red of the data assimilation after assimilating this noisy observation. And we start to see, especially here, that the red curve is very close to the green curve, which is corresponding to the true simulation, meaning that, okay, we start to see that the assimilation using the good catalog here is better than using the bad catalog. So this is the assimilation using the bad catalogs. I think we get some bad forecast, and due to this bad forecast, we have some bad data simulation results. This is just an example to show you in a time series the impact of the different parameterization in data simulation. So now, if we have a look at the global results, so as I said before, we applied the analog data simulation on very local region. So we did independently a lot of analog data simulation experiment, which are completely independent. And you see that even if the data simulation scheme are completely independent, we see a very nice consistency in the results. Okay, so what is this plot? It's showing you a kind of selection probability. So 50% is corresponding to the white. So 50%, it means that 50% of the time we are not able to say if the observation are coming from this parameterization or this parameterization. So here, this is a bad result because we are not able to say if the observation are coming from the good or the bad parameterization. If we are going here, it means that we have a bad selection probability. And if we are going here, we have a good selection probability. So this is the objective. We want to go to this results. And here you see that when we compare the selection probability between these two parameterization, you see that, okay, we start to see some differences, and we are able to detect in some regions to detect that observation are coming from the good the good parameterization. If we increase the difference in the parameterization, now we clearly see that almost everywhere where we have convection, we are able to say that observation are coming from the good parameterization. So this is a very general results in space, but we can also have a look at the details, what is happening in time, especially during a given period of the year. So this is exactly the same results, but we are looking at the selection probability, but for different months. So here we are in December, January, February, and here we are in June, July, August. So we see that the difference is very large in winter in the southern hemisphere, and also in summer in the northern hemisphere when there are a lot of convection activity, especially in Europe and also in this part of the Pacific Ocean. So you see that we are able to detect at given period of the year to detect that one parameterization is better than another one. So this is an important result. So to conclude, I will say that our methodology, yes, is based on a combination of advanced data science methods. I think it can be it maybe seems to be complicated. So this is what I write here, but it's not so much because it's very classic method. So here we we use a very classic data simulation, we use a very classic analog forecast method, and we also use the classic innovation distance. So the combination of the three may be complicated, but it's not in fact. Yes, so the important thing is that what we did here is a comparison of the dynamics in terms of short-term horizon. So this is really something that we have to keep in mind. It's that the methodology is working if we see some differences in the short-term dynamics of the models. So I think the good aspect of the methodology is the local aspect. So we can work very locally in space and time. It's relatively low-cost procedure because we don't need to run a GCM to get some analog forecast. Of course, we need a lot of numerical simulation. So it's low cost when we apply the methodology, but we need a lot of numerical simulation, and the cost is very, very, very important. But if we think about the SEMIP simulation, we already have the numerical simulation. Okay, and yes, of course. So this is something that you need to be careful. Is we need a little bit of tuning, especially when we are looking for the analogs. There is also the inflation and the domain we take into account, and also the errors in the observation. So these are the something that you need to keep into account if you apply the methodology. Okay, so if we go back to this to the main goal of our project. So what I presented before was on the speedy model. So it was a kind of a toy model to show if we are able to detect some good parameterizations, meaning good models or bad models, using historical runs of GCMs. And here the idea is exactly the same in the SEMIP simulation. So basically, we will use the SEMIP simulation in the historical period, and we will try to compare the real observation of climate indices in black here. We will try to compare this observation to the SEMIP simulation. So here I just show you 3 simulation, but in the SEMIP simulation you have maybe 20 models with 20 members and for different scenarios. So you have a lot of numerical simulation. And the idea is try to compute the weights, and when we have some weights saying that one simulation is better than another, we will be able to get some weighted projection of the climate indices. So this is the next step of our methodology, trying to apply the methodology to SEMIP simulation. But we have to take into account some important I will say a recommendation done by experts in climate simulation, and this is very nicely presented in this paper when they talk about weighting simulation, and they talk about something that you need to keep into account. So first is the interdependence in the models, because there are some groups of models and they share some big parts of the code. So maybe some models are saying the same from different climate indices, and this interdependence have a strong impact if we want to weight the simulation. So we have to keep into account this. We also have to think about the performance of models, because there are some models which are very, very good to predict climate indices, and others which are not good to predict climate indices. So this is illustrated here because you see that there are some biases and there are a lot of differences in terms of variability in the CEMIP simulation. So here I show some different CEMIP simulation of an important oceanic climate index, which is the AMOC, and you see that the simulation are very different. There is a very strong bias in the simulation, and also the variability is completely different between two model runs. So this is something that we need to account, is to to remove the bias in the simulation and to remove the artificial variability in the time series. The idea is try to work on on the same kind of signals for the different simulation. So these are the important things we have to keep into account in our methodology. So to do that, I think we can, if we focus here, we can work first on the interdependence. So meaning instead of working on independent different CEMIP simulation, we can work on groups of CEMIP simulation, because if there are some interdependence in the simulation, we can say, for instance, that model A and B are the same or almost the same, so they will be used as a same catalog. So we can do a kind of cluster of models and work on catalogs of clusters of models. Secondly, we have to focus here on that part, meaning that, as I said before, our methodology is working only if we find some differences between two consecutive times and short terms DT. So this is the case here because we can see some difference in the extremes, but this is something that we need to find climate indices between two consecutive times which show some differences in terms of CEMIP simulation. If we don't see some differences here, we will not be able to find some to put some weights in the simulation. So this is an important point. And finally, the metric we use here to define the how close are the forecast and the observation is maybe simple, and we assume here Gaussianity in the distribution of the observation and in the forecast. And this is a very strong assumption, especially if we are working on climate indices, because they are maybe not Gaussian. They can be with, for instance, very heavy tails or distribution, or it can be bimodal distribution, etc. So this distance will be not anymore valid, and we need to think about something else. So this can be a solution to work on optimal transport and Wasserstein distance. The Wasserstein distance is the minimal effort to go from the observation distribution to the forecast distribution. So this can be a more flexible matrix we can use. And of course, we need relevant observation of climate indices. And this is not always easy to get the information of the climate indices in the historical measurement. And also there are a lot of noise in the satellite and in situ measurement. And we need to this is very important to know very precisely the level of noise we have in the different observation. Okay, so this is my last slide, just to explain you that this is a really ongoing work, and this what I presented here it has been presented to a ANR French funding program. So if you have any question or remark about that, I will be happy to have your feedback. Thank you very much.